Hi, I'm Janet Luhmann, and I'm at the Space Sciences Laboratory at University of California, Berkeley. And there I'm a senior fellow doing research these days mainly on heliophysics, especially the stereo mission, on which I'm a PI for the in situ measurement package called IMPACT. And I also work on planetary things. And we have a new Mars mission called Maven. That's a very big part of the LASP organization here in Colorado, and many of you who are associated with that may have heard of it. That's exciting solar wind Mars interaction science that we hope will shed new light on some interesting aspects of space weather. So that's why I have the topic I have today in my introduction, which is to remind everyone that solar wind influences are not just for Earth. And so Sarah gave you a very nice introduction for heliophysics topics such as coronal mass ejections up on the upper right, and the corona shown in X-rays on the lower right with all of its glowing arcades, magnetic arcades, and the corona seen in eclipse on the upper left, where you have the dense streamers of material trapped in closed magnetic loops. And she mentioned that where you don't see those streamers in particular, there is material flowing outward and becoming part of the interplanetary medium. And we know that this hydrogen plasma component of the solar corona that flows out and fills interplanetary space is affecting Earth in many important ways. She also pointed out this type of magnetospheric interaction picture. This is a computer simulation that was done many years ago by Chuck Goodrich of a magnetic storm occurring in the Earth's magnetosphere as a result of a disturbance in the solar wind coming by. And this was actually driven by measurements of the solar wind upstream of Earth. So the real conditions of solar wind density, velocity, pressure, and magnetic field were used to drive this numerical simulation of the solar wind Earth magnetosphere interaction. And you can see that it's very bursty in nature and very time dependent and dynamic. And in that little round inset, blue inset in the lower right corner, you see the model, what the model says is going into the upper atmosphere. The energy flux that comes from the magnetosphere from that solar wind interaction and enters the upper atmosphere to produce heating of all kinds affiliated with physics that you'll hear more about later in the week, the aurora and convection, ionospheric convection. So we know that Earth has this space weather resulting from the solar wind, and there are many different ways that it manifests itself and many reactions that the Earth has to it. Everyone knows about the aurora, and you even get aurora here in Colorado sometimes, and even in the equatorial regions during really big storms. But we unfortunately don't see the aurora very regularly where most humans live. And I always felt that if the auroral zone could somehow be moved to lower latitudes, there'd be a lot more general interest in space physics and solar wind interactions. But we've made a lot of measurements around the Earth, and we know that it's not just the deposition of energy that occurs, but the reaction of the upper atmosphere to that deposition of energy includes important things like the escape of atmospheric species into space. And this is one very important thing that you'll see is affecting not just Earth, but other bodies in the solar system. So the solar wind interaction has a very special way of depositing energy into atmospheres, and the atmospheres react in certain ways. And one of the ways is outflows of species such as oxygen and helium and other upper atmosphere constituents. So we know that the Earth has an ionospheric outflow in response to the solar-wind interaction, which you'll hear much more detail about. And the processes that cause that outflow and all the heating are very complicated. And I just included this complicated picture to express that concept rather than to expect you to understand all of the details at this point. And there are experts who will be coming through who will tell you about wave-particle interactions, who will tell you about double layers that drive auroral particle acceleration. They will tell you about the polar winds that are a reaction to that solar wind energization of upper atmospheres. Now, as I mentioned, I'm part of the STEREO mission. STEREO stands for Solar Terrestrial Relations Observatory. And it was launched in 2006 and has since been making pretty consistent measurements up to recent days when it had to go through a superior conjunction, and we were not able to get the signals from it because it was essentially going behind the sun. And we've also had a problem with the spacecraft, but otherwise it's still operating. And it's still producing very valuable data. And what it does is it sensitizes us to the fact that the solar activity and the reaction of the Earth to it is not all there is, that there's a heliosphere-wide, an interplanetary activity level that is occurring all the time in reaction to the solar atmosphere conditions and the energization of the outflows. So we are now in an era when we think of space weather as not just for Earth. One of the things that STEREO had was a whole bunch of imaging that went from the kinds of extreme ultraviolet pictures that Sarah showed you, that is that little green dot in the upper left, the sun itself with its coronal glowing arcades. It had coronagraphs, which occulted the disk, and so that you could have a solar eclipse going on all the time and see the corona and its activity in all its glory. It had different stages of coronagraphs that were nested on each other so that you could actually follow that very dim light all the way out into space, all the way to the Earth, in fact. And STEREO was a twin spacecraft mission on top of that, launched from Earth, which is in the bottom, the very bottom of that Earth orbit that you see around the sun in the lower left. STEREO cones of fields of view of some of the imaging devices are shown. We could see the sun from many angles with STEREO, and that was a first, that we could actually do stereoscopic imaging, the 3D imaging of solar and coronal structures. And because of that, we began to realize that the sun has a far side, that in fact it's a globe, and just because there's not a lot going on the visible disk doesn't mean there's not a lot going on the far side. And some of these, the big activities, which you will hear about, have global impact. So the fact that we can now see the far side of the sun because of STEREO being there has really made us think more holistically about solar activity and its effects on the interplanetary medium, and to think about it in 3D. This is a cartoon of the evolution of the STEREO ahead and behind spacecraft as the orbit, as their locations with respect to the Earth. In Earth's orbit changes with time, and you can see they move away from the Earth. 2007 is right at the Earth, essentially, the real start of the Heliophysics mission, and 2015 is at the top. And that's what I was mentioning, that the signal that we were getting from STEREO was corrupted for months because of the fact that the sun was in the way and the corona was in the way. And now we're beginning to emerge from that condition and getting STEREO back. So if you go to websites and you look for STEREO data, you'll find that STEREO took a vacation, essentially. Now, the layout of the kinds of heliophysics measurements that we can do, given this new global perspective, is illustrated here. What we've got is a cartoon of the sun and one of those coronal mass ejections coming out. The flux rope you see is extending into space toward the Earth's orbit. This is a very simplified view, but it's one that's very often used because it has all the essential parts. And what that expanding coronal mass ejection does is it launches a shock wave if it's going fast enough and is strong enough in its internal pressure content. And what we have on stereo and also upstream of the Earth in particular, and also in some other missions that are out there making measurements around planets and in the interplanetary medium, chasing comets and so forth, are in situ instruments. They measure plasma, they measure magnetic field, they measure energetic particles. And these are just some insets of examples of what those time series of in situ data look like. Now, in situ folks are always challenged. They don't have this wonderful image draw. But those data, those squiggly lines, are just as important as the images. They're just more difficult to communicate. But they are the things that actually tell us what is happening physically at Earth and in other places. So when you see a mission being designed and you wonder, oh, why do they bother doing anything else but images? I'm hoping that you come away from this school, if you don't already appreciate the fact that spectra and squiggly lines, time series of different components of the plasma and magnetic field are in fact an integral part of space physics, space science, heliophysics that we must understand and integrate into the larger picture if we are to make the physical connections that need to be made. Now, because of stereo, as I mentioned, we know that how things are in very different places in the solar system. This movie on the upper right is just giving you an idea of how the orbit of stereo, which are the blue and red spacecraft there in Earth's orbit, have evolved during the time period up to 2012. And what I have on the lower right is a plot of the occurrence of the interplanetary signatures of coronal mass ejections at the Earth in the middle, seen by the ACE spacecraft, and at stereo ahead in the red and stereo behind in the blue versus year from 2007. And what you can see is that the interplanetary coronal mass ejection count that each site experienced is somewhat different. So it really matters where you are. Just because Earth sees one thing doesn't mean that Mars isn't seeing another thing. And that is something I hope that you will go away from this school with that picture in mind. We have tremendous capability, as I mentioned, for practical uses. If you're interested in solar energetic particles, for example, this is a real-time display, which, as I mentioned, has gone away for stereo for now because of the superior conjunction. But there's plots here from the NOAA Space Environment Center showing you energetic particle fluxes versus time for a week. And these are constantly being updated, and they come down immediately, essentially, from the spacecraft, except for the time, light travel time. And in the bottom is the ACE plot, and you can see there's hardly any energetic particles. Each trace is a different energy of energetic particle. Whereas at stereo was seeing quite a bit of activity, and it was rather far around during this particular snapshot of conditions at the time. So now we can put these pictures together. That cartoon I showed you of stereo and laid out with the images and the time series is a reality. We can do this real time, and we can do retrospective studies of how this all fits together. So you can really see the whole thing. So the bottom line and take-home message here is that not only Earth, but the entire solar system lives with its star. And we now have the capability of seeing the sun in all of its glory and of understanding what's going in each direction and what it might mean for different missions in the heliosphere. Now, a nice illustration of how this applies across the board is this image of a cometary tail disconnection. And what it shows is that, very poetically, comets were originally used to identify the existence of the solar wind. And now we can actually see solar wind activity here affecting the way a comet is interacting with that outflow of the solar atmosphere. And an artist illustration of what they think is happening in terms of field lines reconnecting behind the comet, which has mass loaded the solar wind with its own ions and carrying it away forever into space. So we have a support system, a situational awareness now for things like cometary missions, as well as all the planetary and Earth missions. So an outstanding major question that's still open in solar system science is whether magnetic fields matter. We have here a family portrait of the habitable zone around the sun, and Earth is in the middle, Mars is to the left, and Venus is to the right if you don't recognize them. And they're to scale, but the distance between them is not. The big question that periodically surfaces, and you'll see written about with various viewpoints and is highly debated in some circles, is do magnetospheres really matter in planetary habitability and the way a planet evolves and what happens to it ultimately? Should you care? You know, many people go through life, they don't ever hear about space weather. They don't even hear about the Earth's magnetic field or solar activity. And, you know, the sun is this big glowing ball in the sky, and as it rises and sets every night, and that's the end of the story. But there are things that have happened over the 4.5 billion years of our planet's history, and we are here at this particular point in time. And so it's nice to know what makes a planet get to where it is as a function of time. That relates also to these exoplanet studies that are going on now that we have the Kepler mission discovering things daily. We know that the Earth's atmosphere is residing mainly within this deep bubble of its magnetic field. And that just makes you think of protection, but is it? On the other hand, for Venus and Mars, we have situations that are more like this, more cometary in nature. Because these planets, we know from missions to these planets in particular, don't have strong planetary magnetic fields like the Earth's global dipole that keeps the solar wind at bay. We have a direct interaction of the solar wind with the upper atmosphere. And because there's ionization processes going on in particular, because the solar wind magnetic field gets very close to the planet and penetrates the upper atmosphere, we have some direct scavenging of upper atmosphere constituents all the time. Now, it happens today at a relatively weak comet rate, but this has been going on for 4.5 billion years. So if you add that up, do you get something significant? And so this is a question that's occupying a number of people these days. In particular, Mars. You know, Mars is of interest because of its past surface water. It's of interest to humans because of the past surface water evidence, the potential for life, and our ability to explore in detail, quite frankly. Venus is also extremely interesting by getting to the surface and doing things there, roving around, and even taking pictures from orbit is not an experience like we have at Mars. So therefore, Venus has been relatively ignored, which I think is unfortunate because it's another terrestrial planetary direction it took that we should understand. But Mars, let's understand Mars. It's very important to do that from a standpoint of understanding planetary systems in general and what happens to them over time. So here we are with Mars. Mars is known to have localized magnetism on it. It doesn't have a global field, but it has sufficiently strong localized fields that it makes what people think of as mini magnetospheres on the surface, like that cartoon that you see in the upper middle. And that contrasts to the Earth's global dipole on the left. And as a consequence, we ask the question of whether the space-environment interaction has in part determined what Mars is today, its dryness in particular, its climate change, its thin atmosphere. We also want to think of the possible implications for Earth and solar system history in general so far, as well as exoplanet systems. What we do know is over history, the solar conditions have evolved with time, that the sun was probably much more like a solar maximum condition all the time in its early life, at the very least, and that the solar extreme ultraviolet that makes an atmospheric interaction with the solar wind a certain way has probably changed over time, that the properties of the upper atmosphere that are determined by extreme ultraviolet light have changed over time. And so what we try to do is imagine what could have occurred based on what we see today. And so we play a detective game with our missions. And on that basis, we were able to sell to NASA. There's always competition for missions. Everyone has a good idea of an interesting mission to fly, and there are many bodies, and there are many targets, and many things to measure. But there is a core group of Mars scientists who are interested in the upper atmosphere as an avenue for having controlled what happened to Mars over time by virtue of the physical processes that are going on in there and by virtue of the solar interaction with Mars. And this new mission, which was launched just about a couple of years ago and arrived at Mars in fall of 2014, is called Maven. And the Maven mission is something you might hear about in the news, I hope. Our first results are just coming out. But what this looks at is all the different details of the solar-wind interaction and the solar interaction, and it's trying to measure the actual physics of what's happening around Mars that leads to the escape of atmosphere through this particular driver. And we hope that by understanding the details of this escape that we can go back in time and get an idea of this very complicated picture. The processes are not simple. There's chains of things that involve chemistry, involve physics, involve external influences, involve internal influences. And so this detective work of putting this picture together of Mars atmosphere escape and whether over time it was significant is a challenge which involves a couple of hundred people, and it's hopefully going to be at least maybe not solved by the Maven mission, but we're going to have a much better understanding perhaps of some constraints. Because that's the problem, is constraints. We see all this grandiose stuff about what exoplanets are like and what their stellar interactions are like. What is the real thing like? And this is a good example. So this is just a movie of where stereo A and B are with respect to Mars, which is going around on that outer orbit as time goes on. Where are we in the solar cycle with Maven? We're at that point you can see where the very noisy. Real sunspot number is ending in the cycle on the right there. And so we still have, even though we don't have a very active cycle, we still have activity to look at. We have radiation detectors now around Mars. We have on the Mars Science Lander, there's the RAD instrument on the surface that is detecting activity. Maven there on its cruise and now in orbit is detecting solar energetic particles at Mars. You know, how have these affected the Mars surface and its evolution? We have been able to follow conditions during the Rosetta mission. There's other missions out there. There's the Dawn mission at Ceres currently. There's, of course, the Pluto mission, which Fran Bagenal is heavily involved with, and they even talk about space weather out at Pluto, but that's a whole different game. So here are our thoughts to go home with on living with the star science. And the fact is that we are members of the solar system, not just planet Earth, and living with the star science pertains to the whole solar system. And it really is an enhancement of all of NASA's efforts, from planetary to astrophysics to heliophysics. So don't think of it living with the stars just confined to heliophysics. It's one of these wonderful areas that is just very holistic in terms of its application to every aspect of space science that we do. And in the future, I think we need to think about living with the star science from the viewpoint of exoplanets, because exoplanets are going to be very big when James Webb Space Telescope starts operating. Kepler is now in a second phase of its life called K2, where it has specially targeted sun-like stars in the galactic plane, and we can actually do Earth-like planets better than ever before with Kepler right now. So we have the ability with our Living with Star Science to feed into that and to give some ground truth to the people who are looking at planet-stellar interactions in general. So this has been a very broad brush conceptual kind of introduction, and I hope that it has given you just a different way of thinking, which was my goal, rather than any specific science point. But there's a lot going on. It's a very exciting time, and we want you to go forth and multiply and make sure that people do not lose the perspective that we have gained over time by having this wonderful enterprise that we call Living with a Star. Thanks. So I will take questions. Yes.
I have a question. Do you think we could benefit with a stereo C or even a stereo D, because you can't see what's behind the sun that's rotating into the view, and especially where Earth is in its orbit, where stereo A and stereo B is? Could you benefit with a stereo C at least 60 degrees behind the other one? So you can see what's happening, the activity that's rotating into view.
Okay, so the question is basically asking, were the two stereo spacecraft enough? When the stereo spacecraft finally got around to 90 degrees from the Earth on both sides, we were able to see the global sun. Of course, the actual far side meridian was still on the limb, and limb observations are always a little different than disk observations. So ideally, yes, you would like to have as many sentinels around, marching around Earth's orbit as you can, to get the angles right, to get the directions of things right. It was difficult enough to get the two stereo spacecraft, and unfortunately, stereo behind has been having problems since October 2014, and we're not sure we're going to get it back. But absolutely, it would benefit us to have another spacecraft that would fill in any gap left by the two, or at least make it not so that we had some area that was only on the limb, not fully observed. If you're going to do triangulations of things that are going in different directions, you really want that multi-point perspective.
The one thing that it didn't measure was the surface magnetic field, which is highly
Oh.
unfortunate.
Yes.
But we will get some snapshots once the solar orbiter, the ESA NASA mission goes up, hopefully 2 years from now or thereabouts.
Yes.
Can I comment on, just amplify the question she asked and respond to Jared? I think it's a great question. As young people in this community, I think you should be actually thinking about not just cost of missions. There are many ways of achieving some of these observations today. So if you think of the volume of the heliosphere and the number of measurements that we have, it is really insignificant, right? In terms of really trying to assimilate the data, to do the modeling, to do the ground truth validation. So it's just not stereo C and D. I would say just have to kind of have a necklace around the sun, multiple observations, sometimes the same suite of observations, sometimes different, but it is your generation that's going to think about how to achieve this, maybe with small missions, maybe with CubeSats, and to get the observations that we need. So that was a great question.
Yes.
Can I take the opportunity to actually introduce Lika? Because Lika wasn't here when we started up, but Madhumika Kurta is from NASA headquarters, and she's basically led the Living with the Star program into its existence. And about a decade ago, she came up with the concept of a heliophysics goal doing this, and in fact supports all of your presence here. So that's Lika.
That deserves a hand.